Hey everyone, in today's lesson, we're going to be learning about vector projections. It's an application of the dot product. So let's get started. So what a vector projection is, you can think of it like a shadow. So if you think of in this diagram here, you have two vectors, u and v, and think of like a light source coming down from above. The projection of v onto u is like the shadow that V would project onto like the surface that contains U. I think the diagram here does a really good job of that. So the projection of V onto U is this guy, this kind of shadow right here. And we would write this vector as the projection. If it's onto U, we have a little subscript U, and then like so, projection of V onto U. So that notation gets a little bit of getting used to, but whatever you're projecting onto is your subscript. Now, in this case, the angle between these two vectors in the diagram is acute. It's less than 90. And so this vector projection of V onto U, you can see it's going to be in the same direction as U. And in this case, because V is that horizontal component of V is a bit longer than U, the projection is longer. But say if V ended here, then it would be shorter than U. So there's lots of possibilities there. But the big idea for now, vector projection, you can think of it as a vector kind of representing a shadow. So what happens if the angle is tail to tail between U and V is obtuse? So if it's between 90 and 100. And that's, remember, angle between vectors is tail to tail, right? Well, in that case, you can still think of the vector projection onto U of V as like a shadow, except this time the vector projection will be going in the opposite direction. It's still parallel to U, but in this case, it's in the opposite direction. So acute angle, same direction. Obtuse angle, the vector projection goes in the opposite direction. And if the angle is exactly 90, there's not much to add to this diagram here. Much like if you're outside and the sun is directly overhead, you won't see a shadow. In this case, there is kind of no shadow as well. The vector projection will be the zero vector in this case. So let's calculate some vector projections. So here, we're going to project U onto V. So as a little note here, this is for projecting onto V. V is in our subscript. And maybe just as an aside, I might go back to the first diagram. We drew the vector projection of V onto U here. If we wanted to draw the vector projection of U onto V, I might just use green here. And you don't need to add this to your sheet. We would imagine the light source coming in perpendicular to vector V in this case, if we were projecting onto V, and the vector projection of U onto V would look something like that. So it's not interchangeable. The projection of U onto V is different than V onto U. But yeah, let's do a couple examples here. So we're projecting onto, where's my cursor? We're projecting onto vector V. It's a tiny vector. So what I might suggest for this one is maybe just do a little dashed line to extend V. And then we're imagining our light source kind of coming in from this way, casting a shadow onto V. And so drop a little perpendicular there. Not perfect, but that's okay. And at this point, I'll switch back to, actually, maybe I'll use red to show the vector projection. So maybe at home, you can use a ruler. I'm drawing on my tablet here. Actually, that wasn't bad for a straight line. So this is this will be the vector projection of U onto V, that vector there. So a light source perpendicular to V, make a right angle triangle. That's how you would kind of draw it. Now, as to what is the what is that vector? Well, we have to talk about its magnitude and its direction. So what's its magnitude? What is the magnitude of this vector projection onto V? Well, just using trigonometry, it would be the hypotenuse times the cosine of 50 degrees, because it's the adjacent side here. So it would be, I'll even write this out. It's the size of u times cos theta, which in this case is 5 times cosine of 50 degrees, which is about, not 5 cos 50, about 3.2 units long. And for as far as its direction goes, the projection of V onto U, for now, we can just say is in the same direction as V. So we've determined the vector projection. We drew it, we determined its magnitude and its direction. So we've determined that vector. Let's do another example here. So here we're going to project P onto Q. So just getting a little used to working with different variables here in the notation. So we're projecting onto Q. Light source coming down perpendicular to Q would create a shadow kind of like this. So this is the projection onto Q subscript of P. All right, so we've drawn it. Let's find its magnitude and its direction. For its magnitude, if we want to use trigonometry, we need the angle in this triangle. The tail-to-tail angle between P and Q is 120, which would make this angle 60 degrees. So the magnitude, this is the one time a year I use this notation too. So I just have to think and double check before I'm writing things down correctly. Projecting onto Q, it's the size of P, the vector we're projecting, times the cosine of the angle between P and the vector projection. So that is 20 times the cosine of 60. I think cosine 60 is a half. I should probably know that. It is a half. 10. So we've got its magnitude, and we can state its direction. Projection of Q on of P onto Q. Because the angle between P and Q is obtuse, this vector projection is in the opposite direction as Q. What you might have noticed in these two examples is that the vector projection didn't depend at all on the length of what you're projecting onto, right? Where in this question did we use the fact that the length of Q was 30? Or in the previous one, that the length of V was 1? We didn't. If Q was a vector this size, or this size, or this size, we would get the same answer. So the vector projection, is independent of the length of what you're projecting onto, which is pretty cool. And we're going to see that actually because we're going to develop a formula for developing the vector projections for algebraic vectors, because we've been working here with geometric vectors. So we're going to make use of some things we built on here. Let's kind of dive in. All right, so consider here, we're going to derive a way to determine the projection of V onto U. So that would be this vector here, projecting onto U vector V. So what do we know so far? We know from our work with geometric vectors that the magnitude of this vector projection, we used trigonometry and we used cosine, is equal to the size of the vector we're projecting, V, times the cosine of the angle between them. The direction of this vector projection is in the direction of what we're projecting onto, in the direction of U. I just want to mention a couple of things. So this works fine if the angle is positive, because you get a cosine is positive, and so it'll be in the same direction as you. But this definition actually works too. It will work eventually. So you might be worried, well, what if the angle between these two guys is obtuse, then cos theta is going to be negative, and how can you have a negative magnitude? But when it's obtuse, we'll have the direction being in the opposite of you, and that negative will actually flip you around and get us the right direction. So everything will come together eventually. So don't worry about this for now if you're worrying about what happens for obtuse angles. It's all going to come together and work out mathematically. All right, so we are going to put these things together. So to get the projection of u onto v, to get the right magnitude, we're going to multiply by the magnitude. And to get the right direction, we're going to multiply by a unit vector in the same direction as u. So this part is going to give us the right length in the following: 1 over the size of u times vector u is going to give us the right direction. So this guy here gives our vector projection it's the correct direction, and it's a unit vector, right? And this guy gives it the correct size. So putting those things we developed earlier together, we have the magnitude of v times cos theta times 1 over u, magnitude of u, times vector u. So I might bleed into this open space down here, but let's keep going. So our goal is to have a nice tidy formula that we can use. And looking at the left here, we've got magnitude of v, scalar, cosine theta, scalar, magnitude of u, scalar. Let's actually write in our definition of cosine theta from the dot product. So we have the magnitude of u. From our earlier work, cos theta was the angle between two vectors, was the dot product of those two vectors divided by the magnitude, the product of the magnitudes, right? And then we have 1 over u, size of u, times vector u. And check this out. We've got these magnitudes of v dividing out. And I just want to double check we're projecting onto vector u. All right. Projecting v onto u, magnitude of v, just making sure I have everything down here. Yep, everything's good so far. And we're almost done. So on the top here, we've got u dot v. If you guys remember, the magnitude of u times the magnitude of u was actually equivalent to u dotted with u. And then we have vector u on the outside. So if you recall, finding magnitudes wasn't hard with algebraic vectors, but it was, it takes a little bit of work. Finding dot products is really easy. So now, given u and v as algebraic vectors, we've got an easy way to find the vector projection. You find the dot product of u and v. You find the dot product of u with itself. And again, that just gives you two numbers. You take that ratio and you scale vector u by that. So it's actually a really tidy little formula. And it works from this little derivation, a little bit giving it the right size and a bit giving it the right direction. So let's actually put that to use and see that it works. So we're going to determine the vector projection of the vector 2, -3 onto C14. So 2, -3, do my best to make my diagram neat. That's there. That's vector D. C14 is up to here. So if I'm projecting onto, projecting D onto C, actually. So I need to undo that. D onto C. Erase all these dotted lines. So I'm basically getting a diagram set up. We'll do the math, and hopefully we'll see that the diagram and the visual match up pretty well. So we're projecting onto C, which means I'll extend C like that. We'll imagine a light source that's perpendicular to C coming in and casting a shadow. So we're thinking that maybe the vector projection onto D or onto C of D looks something like that. It's like -0.5, -2, like something to that effect. So now that we've drawn a visual, we understand how to like draw vector projections. We've got an estimate of what our answer should be. Let's show that our formula works, and we should get something pretty similar. So using our formula, if I can find my cursor, here we go. We are projecting onto C, we're projecting vector D. So if we're projecting onto C, we're going to have a vector that's like parallel to C. There's vector C there. So you always have C on the outside. And then if you go back to our formula, if you're projecting onto U, everything is U except this little bit of a dot product on top. So in ours, everything will be C except it'll be D. So it'll be C dotted with D, C dotted with D over C dotted with C times vector C. So that's it. So the formula is easy to set up. It just, if you just remember, if you're projecting onto C, everything is C except the one on top. All right, so now we can begin. So you can do this in as many steps as you like to feel comfortable. So C dot D, you might even be able to shave off a step from what I do. So that would be 2 times 1. I just did kind of D dot C there. I did 2 times 1. That's okay. And then plus -3 times 4. So multiplying the coordinates like that. C dotted with C will be 1 squared, like 1 times 1, plus 4 squared, 4 times 4. And then vector C is the vector 1, 4. So what do we get on top? We get 2 take away 12. That's -10. 1 plus 16 is 17 times 1, 4. And then scale that in, we get that the projection of D onto C is -10 over 17, -40 over 17. Whoops, square bracket. Now, to help us visualize that, if you make those into decimals, kind of check your answer, you get about -0.6, and 40 divided by 17, you get about -2.4. Which definitely seems, I didn't draw a perfect diagram. I just did it freehand. If I maybe had a bit more care, my diagram would be a bit more accurate. But that definitely lines up with what our diagram says. So what you guys need is you need a bit of practice getting used to the formula. I would definitely go back and just kind of wrap your mind around the definitions of projections. These 3 cases we have initially do a good job of that. We looked at vector projections for geometric vectors, again, to kind of cement the idea of what a projection is. And then we derived a formula for algebraic vectors, because we've seen that when vectors are in algebraic form, all these operations, there's often a nice tidy formula that works and is not too bad to use. And you can save yourself a great deal of work. In our final example, we got a visual of the projection, tying that in, and then we verified the formula works. So you guys need some practice drawing projections, using the formula. The practice I have for you guys today, that is a lot of practice there, but as usual, just do what you need to do to feel comfortable. So if from 1 to 14, if you think that's a lot and you find a question or two repetitive and you think, yeah, I've done that, I'm comfortable with that, then just go on, right? Like, you guys know the drill. All right. I hope you enjoyed that lesson. I really enjoyed teaching it. Hope you guys are staying well. The weather is great. So, don't do calculus and vectors today. Make sure you get outside and enjoy the weather. This can wait. We'll see you guys soon.